Okay, so good morning. Let's go back to
where we stopped, which is Laplace's equation.
And what I want to do, so we have Laplace equation, right, like this. And some omega. Let's think first that we have a smooth boundary. At one point, I will consider corners. And what our goal is to find the Green's function and then, let's say, use it to our benefit. So let's find the Green's function. You'll see what the Green's function is and find it to our benefit. So we're going to use it in a nice way. Okay, so first, it's almost like if I hadn't told you I was looking for the Green's function, I think it's good to say is we can write we can write Laplace's equation in, let me put it, with spherical symmetry. Okay, that is spherical coordinates and only, let me put it here. Yeah, I should write. So, spherical coordinates and only keeping radial dependence. Okay, so it is invariant under translation and so on. So namely, we look for a solution V equal C of R, which is the radius, right? Where R, let me define R. The notation is this, okay, which is so that we remind ourselves in what dimensions we are. This is the same as, let me dot, 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 continue here. This is okay, up to maybe number here, n, right? Remind a dimension. It's centered at C. Oops, I forgot the 2 here. Centered here. This will come in later, and then. Okay, I'm not going to deduce this a little bit. Even in Fritz John, for example, I'm following Fritz John. It's only indicated, it's not deduced. We can write the Laplace operator. So let me make sure I make the n and the r's different, because writing quickly, sometimes they look the same in my handwriting. We have this. Okay. So in dimension n, we can write the Laplace's equation. So this is n. Laplace operator like this. What would we do? So, right, there's some, it's a lengthy calculation, right, to go from here to here with all the thetas, and then I ignore the theta because it's independent, right? Because of the radial symmetry. So this is nice. This looks simple. After, say, a lengthy calculation, this is simple. And this is basically, we can think of this is basically, right, like this. This is basically the ODE W prime of R 1 minus n over R WR, right? Because it's derivative here, derivative, trivial change of coordinates. I mean of notation, I didn't coordinates, sorry, I said it wrong. So WR, if we integrate this twice, we get this. Where W is C prime, and therefore, right, here's just so you follow my just change of this, where, well, let me put it here, to give, or to yield the following result. Which is a nice result that we will be using in connecting with many things, as you will see. So this is a capital C. Okay, so, right, I'm already telling you that I'm in search, looking for the Green's function. Well, I already know that the Green's function is like the operator acting on U, giving me the Dirac delta function, so it has a singularity, blah, blah, blah. Okay, it's usually has radial symmetry. So what did we do? So we looked at Laplace's equation in spherical coordinates. We integrate it, and it looks good. It looks good because it has a singularity, right? But now we have to check if the singularity is doing the right thing, right, to give us like a delta function, right? Which is a little bit the Green's function, is like you put an impulse here, and you see how the medium, the problem reacts to that information, which is the delta function there, and that's very useful to invert operators and so on. We'll see that. Okay, so let me put here, this function has, which is nice, right? Singularities, when well used, they are nice, which has a singularity at x equal to c. Okay. Now, so telling you what we're looking for. Now let's check the nature of this singularity, right? To see if it's if it's a good singularity. And correspondingly, let me put this as from the notes, almost forgot, and correspondingly, find the value of the constant C. Okay, so how do we do this? Okay, so we have this function. Let's see if it's good for our use. So take a ball centered at C. Let me put it like this. Just epsilon small, a ball centered at x equal to c. Okay, let me call omega of c, not c, sorry, omega of epsilon, omega minus the ball of radius epsilon centered at c. So let me do a little, because the figure is over there, let me do another picture of our domain. This is a boundary. This is C. This is our ball of radius epsilon centered at C. And we're going to think of our domain for this analysis as this. And we will allow the epsilon to shrink to 0. Okay? So it becomes a punctured domain. Okay, and then we're going to sort of extract the effect of the singularity and see that actually we have a good singularity. You see what I will mean by a good singularity. Okay, so let me see if I have the information for you. Ball centered at C radius epsilon. This is our sort of a domain with a hole. Okay, and Green's identity, here it comes. I mentioned we're going to have many versions of Green's identity last time. Let's write the standard, let's say the first one, for this domain with a ball, with a hole. Okay, so this is Green's identity in this domain, okay, where, no, here is wrong, my notation. S of epsilon, which is the contour here. Sort of the spherical shell of radius epsilon, right? Because the ball, yeah, okay. Which is the same as, right? The same as if. Okay. And we are actually, eventually, we want to shrink, as I mentioned, this to 0 and see if we capture, right? This is done many, many times in different situations, capture the effect of the singularity. Okay. Now, we're going to consider as U to be a smooth function, right? So, say, at least U is C2 up to the boundary, and V, we're going to take V to be our candidate for the Green's function. Okay, let me already announce this, right? Our candidate for the Green's function. U is just a smooth function, okay? It does not have to satisfy Laplace equation, it's just a smooth function with enough regularity so we can play with it and so on. Okay? So let's we're going to start looking at these terms here in particular near the ball, okay? Because we want to take the limit as epsilon goes to 0. So let's play with some individual terms, and then we put all the information together. Okay. let me actually, sorry, I'm going back and forth. Let me actually put some more information here, is that let me put some more information here. Well, maybe not, sorry. Let me see if I can keep in this board so the camera follows me and we don't. So at S epsilon, which is the boundary of the ball, B is basically a constant, right? This function is spherical symmetry, so it is basically this constant. And dv dn is this right, just by computing there. So now we have the following. Note that. So I'm going to do some approximations using order epsilon and so on for the boundary terms of my Green's identity, okay? So the first one is this. Note that the integral over S epsilon of du v du dn ds, because I want to shrink this to 0, right? So I need to look at the border of that ball. Well, this guy is equal to c of epsilon, the integral of du dn ds, which is equal to c of the epsilon. Sometimes my epsilon looks almost like a c. I have to be careful. And the integral, I put a parenthesis here, minus the integral over the ball of du dx. So what did I do here? Okay? Simple, right? So again, let me highlight what I'm checking, okay? Well, my main goal here is to see what happens when this ball shrinks to 0. It's like a zoom, right? Shrinks to 0, and I see what the singularity gives me, right? Maybe things can blow up. Maybe things can go to 0. Maybe there could be something non-trivial. One part will go to 0, and another part will be non-trivial, which is good. That's why I said it's a good singularity. So I want to zoom this into 0. Well, if I want to zoom this into 0, in this integral here, right, in Green's identity, I have to highlight this. I think it's good to highlight this because this is our main object to look at. So when I zoom in, right, this part here is the part I have to be careful. In particular, here where I have derivatives, maybe things will blow up. I have to check what happens. Okay? So that's what we're doing over there. Right? Okay? Here, this is basically going to be a domain with a punctured domain. We'll see. We'll see what's going to come out. Okay? So where was I? Okay, here. So here, look at this first part of the boundary term. Very simple, right? This guy, which is this guy, is constant. So I pull it out of the integral, right? It's constant because of the spherical symmetry. This guy, to give me this, what is this? Nothing more than what theorem did I use here? Divergence theorem, right? So this is just divergence theorem, right? This is a grad u scalar to the normal, divergence theorem. Okay. Now, so let's leave it at this. Now we also have this, the integral S epsilon of u dv dn, okay, is going to be equal to minus c epsilon 1 minus n S epsilon u ds. Okay, because this is the derivative that we computed above, and we have this simple thing. Okay, now we're going to do approximations. Okay, now let me see if I can organize this in the blackboard. That's what I'm looking at, so I can save space. Okay, I think I can do this here. Now the fact that so remember, epsilon much smaller than 1, right? This is important. And for very small, we're shrinking it to 0. So here, look, I may write this like this. This is approximately see if I can squeeze it in here. And let's see if you can guess what I did. What did I do here? It's an approximation, right? I'm saying, well, this is this, and this integral here, right? I'm approximating it by this guy evaluated at the center of the ball, and something which is order n epsilon to the n, which is the volume of the ball. Which means I don't even have to write the expression. We know what the expression for the volume of the ball, but we don't even have to write it because we're just controlling what we're controlling. We're trying to control a game here, which is a dispute between orders of epsilon on the numerator and, say, orders of epsilon on the denominator because of the psi, right, of the singularity. So that's the fight. It's a fight between only what we have to control somehow is a fight between a dispute between orders of epsilon. Okay? And this, at the end, will be this part here. Let me put it like that. Yeah, so I can save space. This is going to be gradu xi order epsilon square, right? Because of the psi and its powers of epsilon. Okay, the other guy, so check this on your own time. This one I can approximate like this. This is going to be minus c epsilon 1 minus n. Right? It's right here. It comes from the derivative of the candidate for the Green's function. Okay? And the same thing here, but now I'm going to be a little more specific. I'm going to write this u of xi and omega n epsilon n minus 1, where this is important, where this is the area of S epsilon, the area of the ball, okay? The area of the ball where this is the area of the unit ball. And it will come in. That's what's going to define our constant. Area, unit, sphere, and this is the gamma function. Okay? So this is the guy, which is the interesting guy. So can you see where we're going now? When we zoom, when I do the zoom, okay, let me release my hand. When I do the zoom of seeing what the singularity is doing, the zoom is here. The ball near the singularity is shrinking, 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 shrinking. And I said it's a good singularity. You will see why. We're about to see why. Because something will disappear, which is not so bad. It really would be bad if something blew up and I can do nothing about it, right? But something will disappear as I zoom in, and something will remain finite and interesting, as you will see. What will disappear is the first part, right? Let me highlight this. As I zoom in, this part will disappear. Now here, look at this. Let me put the epsilons in orange to highlight. As I zoom in, what happens? These epsilons cancel each other. There's one in the numerator and another one in the denominator. And I can see which is a good value for my constant, so that at the end I am left with a function value at the center. So if I calibrate things properly, right, these epsilons give me something finite, which is a good thing. So there is a cancellation, right? There's a balance of epsilons. And if I put that function, that singular function's constant, 1 over the area of the sphere, basically as I zoom in, what do I see there? I see the function value, that's good news. Okay, I see the function value. Okay, so let me write this. So as we take the limit with epsilon tending to 0, we obtain this. And now, sorry, I have to put this. I mentioned this, but I didn't write it. Where we used this constant. Okay, and now take and you will see this later on, maybe not today, I don't know, maybe we'll see, maybe not. Take U to be what we call a test function. Which is a function which is smooth, right? This is C, which is infinitely differentiable in compact support. Test one. To conclude, that, and maybe I'll write it here to see if I can squeeze it just so we keep it on the same board. And in a little while, maybe this class or the following, we will highlight a little more, right, when I mentioned a little bit about distributions. But look what's happening here, okay? So eventually, I'm going to define I'm not going to do much in terms of things with the notion of distributions. These are things you see more in the course of function analysis applied to PDEs, which is the linear theory, okay? PDE's linear theory. But I'll give you a little bit of an indication, right? What is a weak derivative? What is a generalized function? What is a function in the sense of distributions and so on, right? It's something in an integral fashion. So we already arrived at the first instance where we're seeing the generalized function, right? So if I get this expression here, right, which we just deduced, let me put this one in yellow. So we have understood, see, let me release my hand so I can explain better. We have just understood that basically we got the Green's function for the Laplacian. Why did we get the Green's function for the Laplacian? Well, we got something which actually, if the operator acts on this function, it gives us the Dirac function. From an applications point of view, the delta of Dirac is like, I have an impulse here, this generalized function, and I see how the solution reacts to that. So it's right. So that's and we can use that sometimes to invert the problem, to solve the problem. We'll see this later on, right? To write the solution using the Green's function. But right now, what we did is we use Green's identity, which is integration by parts, right? So I'm going back to last class and using words. We use integration by parts to write Green's identity. Green's identity, I can play with the functions to get things out of it. Remember, I did v equal identically to 1, and I got that compatibility condition. Well, now I used this function with a singularity, which is v, to show that it is a Green's function. That is, the operator acting on that function gives me the delta, the Dirac delta function. So here it is. First thing is that when I did the zoom, that integral part gave me the function value, right? And we kind of know that, and we'll see this, that the integral of a Dirac function acting on the function gives you back the function value at that point, right? For those who are, for example, and we have here students that are interested in probability, right? It's like having a Gaussian distribution, and when you go to a Dirac delta function which has total mass 1, that's an absolute certainty. You have the function value there, the average, right? There's no uncertainty if you think of a distribution. But here it's just the Dirac delta function with no meaning, right? No probabilistic meaning. And this is the expression we have. Now, weak derivatives, I'm going to give you the definition of weak derivatives soon, is that it's in an integral form and we use test functions because the function does not have enough regularity to have a derivative in the usual sense. Okay, so we use test functions, and test functions are smooth functions of compact support. Here's the notation, continuous function, infinitely many derivatives, compact support. We use it as a test function, and usually when you do weak derivatives is you use integration by parts. I'll give you the definition soon, maybe today, if not next class, which is you throw the derivative by integration by parts on your test function, And therefore, you get a better notion of differentiation for functions without enough regularity. We already saw that, like shocks is already a function which doesn't have the regularity. We already saw that. So if I use this test function here, in this expression, I get this. Why? I did a jump. I went fast. But it's simple. This guy disappears. Because since this function has compact support, right, it has nothing on the boundary. Because its support is inside the domain. So it's already 0 on the boundary. Okay? So this term disappears. And I'm left with this is equal to that. Here it is. Okay? So this is equal to that. That's just this using the test function, the notion of test function. I don't see the boundary anymore. Okay? Now this integral form, and we'll see this as a functional, this can be written like this in a short notation. This is just a short notation of this. What happened here? I am saying, so let's look at the short notation first, okay, as a functional, right? As a functional, that's why I'm using operator notation here, is that this functional, Laplacian of v, acting on a function, on a smooth function, gives me the Dirac functional, which is the integral. This is a short, and I'm going to say in words, this is short for the integral of the Dirac with phi, which gives me back, here it is. Look, this is a short for this. It gives me back the function value at the xi. This is a very short notation for integral of phi delta dx, which gives me the value at the point, right? And this is what will appear soon as our definition of a weak differentiation. In this case, weak derivatives of all the derivatives of the operator, because I have sort of integrated by parts, right? The Laplacian, basically, if you integrate by parts, its adjoint is the Laplacian. So I threw the Laplacian from v onto my test function, right? And I get the Dirac. So therefore, this is the same as this, which sometimes we're just going to write this. The Green's function, maybe I'm going to call it with a capital G. So this, sometimes I'm going to write it just for short like this. Right? Where here I am hiding which point the delta, because it can be just any point it can be any point in my domain, right? It doesn't matter where I put that ball. Here. It could be, this is true for any point in the domain. Okay? So this basically defines our Green's function. And I'm going to do calculations in the near future, maybe even today, whatever, where I'm going to use this fact, right? That the Green's function solves this equation in a generalized form. Okay? So therefore, let me go to the next board. V is also called, V is the fundamental solution of the Laplacian, and also is and you see why I call this free space. You will see this later on. This free space Green's function, because there's not a unique, right? There's not a unique Green's function, as you will see. Okay, so different notations. Different notations is V is equal to this capital K of X and Xi, also this Psi of X minus Xi, and also, as we have just used, this, okay? So usually, sometimes I even put here a column, which means this is like a parameter. It says it's the Green's function as a function of x, but which has the singularity located at c. So this is basically, we can think of this as location of the singularity. Okay? So, in essence, right, what this does is that we can write this also like this, right? For all right, this is the same as was written right here. Okay, now let me show you some interesting sort of physical interpretations we can take out of all this sort of, at some point, weird or funny looking function, right? Because it's not really it's a generalized function distribution. So let's look for, note, for n equal to 2, dimension 2, that the singularity is logarithmic. So that is, it's a weaker one. Not as strong as for n greater than 2, or greater, let me put it like this, greater or equal than 3. Okay, we can just look this, right, up here. Right, a logarithmic integral is integrable. Now, another interesting thing. Let's use Green's identity with U in C2, say all the way to the border, a harmonic function. So U now satisfies Laplace's equation and our Green's function, and V equal to namely Laplacian V equal to delta. We get what is called Green's third identity. Okay, so let me highlight this for you. Green's third identity is Green's identity with the choice of a harmonic function and the Green's function. Okay? And look what we get. This is very nice. I like this very much. This expression is very nice. Let me highlight and discuss it with you, right? In many ways. It's worth spending some time here. So look at this. This formula, so again, let me put a drawing here so we can discuss. This is omega. This is partial omega. And this is our line integral over omega, in particular if we are in 2D. Yeah, but I'm not in 2. This is basically in 2D. We have a line integral. Okay, but this expression here is it's independent of the dimension. Okay, so maybe I should actually erase this for the time being, not to confuse. Let me just do this. So look how nice this is. This says the following. I have X on the boundary, and I have C in the interior. So look what this nice expression does. This Green's third identity says that I know the solution to Laplace's equation I know the solution to Laplace's equation at any point if I know the Dirichlet data and the Neumann data. The problem is that we usually don't know this. We either know one or the other. But we're going to see there's an equation we can write, we can cook up to basically find one from the other. Not always that easy numerically, but possible, okay? So there's a functional relation. So this is already a very nice expression that tells us that indeed, even though Laplace's equation is a second order equation, right? And for the wave equation, we were able to give as information the function value and the first derivative. For Laplace's equation, we don't have that freedom, okay? We cannot give the function value and the first derivative, right? But if we knew both of them, we solve the problem. We know the solution anywhere inside. All we have to do is to compute this integral along the surface, right, with the Green's function. So look how the Green's function is already giving us interesting information. Okay? Now, this, in particular in 2D, as easy to show, this is basically known in physics also coming from electrostatics, okay? This is known as a single layer potential, like, for example, charges. It can be a positive or a negative charge, okay? So from physics, so it's a potential in the sense that it's connected with Laplace's equation, but it has a singularity. And if the singularity is positive, it's a positive charge. If the singularity is negative, it is a negative charge, right? This is from electrostatics. I have to stop and breathe, or else I can say electrostatics. I say it wrong. Okay, well, where's the sign? Where is the sign of the singularity? It's in here. So the Neumann data can also be interpreted as a density of charges, right? So wherever this function is positive, I have a positive charge. Whatever it's negative. So you see, look at this. As I'm moving along the boundary of my domain, this expression physically, right, is telling me, because I know that the Green's function has singularities, this part here is telling me, the first part is telling me that that from the physical modeling point of view, I can think that I have distributed a density of charges along the boundary, right, where the density is given by this function, right? So this function basically, right, I'm not going to write it here or else it's going to be, I think, get too messy. But remember, if you go back to last class, I wrote, I think actually exactly on this board that I wrote that the Neumann problem, I had that the normal derivative was equal to g of x. And that the Dirichlet problem, the Dirichlet data was equal to f of x. Right? So let me write this here. Actually, it's good. Look, if I change this to f of x, and I change this to g of x, I think it's good. G of x is my density, that is my distribution of charges along the boundary. So you see, this problem is kind of cool to think of it now, having in mind the Green's functions, that I can put singularities on my boundary, or charges on my boundary, if you like, and that will help me to know, right, if I put the right ones, I'll know the solution inside. Now, let me put the orange. This guy here, from physics, right, from the electrostatics point of view, this is called a double layer potential, okay? And this F here, instead of being the density of charges, is the density of dipoles. Okay, so usually charges is something that we usually view in physics books like this, right? Sort of a positive charge. And the dipole is one we let a positive and a negative charge collide without canceling. And usually a dipole is something that looks like this. So it's called the double layer potential. The name double layer potential is because it has two layers of singularities, right? A charge is just a single layer of singularities, and a dipole is a double layer because it's a positive and a negative charge colliding without canceling each other. So if you look in physics book electrostatics, you see this, and it looks like that. So that's why it's called the double layer potential. And the F is the density of the double layer potential, meaning if its intensity, in other words, is positive or negative, which is this or flip. The same way the charge can be positive or negative, right? Which means it's coming in or coming out, whatever. If in fluids, this is a source of mass, and the negative charge is a sink of mass, like mass is being taken out. So this expression here can be interpreted in both a purely mathematical fashion, and I will repeat this, or in a more physical fashion. So let me repeat it for you because I think it's instructive. At least I like it, right? I like applications. So the purely mathematical fashion is this. It relates, it has a connection with the Neumann data and the Dirichlet data, okay, together with the Green's function. That's the purely mathematical fashion, right? And I'm going to give you more information in just a second. So what it says mathematically is that if I receive proper information about the Dirichlet data and the Neumann data, which is usually not easy, but maybe I get it as a birthday present, right? Somebody solved it for me and gives me both information, I'm done. I don't have to solve the problem. Because if I know Dirichlet and Neumann, I know the solution everywhere. No work needs to be done. The only work you have to do is to integrate this. And sometimes you have to integrate this not by hand, but numerically. Right? So you're done. That's the mathematical interpretation of this formula. The physical interpretation of this formula, for example, in electrostatics, is that you know the solution, sort of the potential, whatever, if you put a distribution of charges and of dipoles along the boundary. Okay? So if you set your singularities properly along the boundary, you know your potential inside. Okay, so that's the interpretation. So let me do in 2D another interesting thing that will connect us with complex variables. Okay, so let's see this. Where's the eraser? I forgot it there. Sorry. Let's do a simple case in 2D. And now I want to do the following. I'm going to take my point C and I'm going to allow it to go to the boundary. But to do that properly, mathematically, I then have to do similar to what we do in residues to deform my boundary. So now I do have a contour integral okay, so let's see what happens. Okay. So I'm going to allow, right, this to happen. So what I'm going to do is this, allow C to go to the boundary. Sorry. To move to the boundary in where? In Green's third identity, the expression we had over there. Okay? So, as an exercise, so in a I'm not going to do it in all generality. I'm going to give you the result in all generality, but I'm going to just show to you in a schematic, simple way so you believe what's going on. So in a schematic, simple configuration, consider this, or not let that, consider the interval minus L, where I have this. So I'm going to say that C is equal to X bar. Excuse me. The radius here is epsilon. I'm going to call this part of the contour gamma epsilon, and I'm going to call this contour omega L. And let me write Green's third identity, at least the part I'm interested in, like this. Okay, so this is, let me write here, right? This is the relevant term of Green's third identity. Okay, the important one. So this log of R is, here it is the Green's function, right, for n equals to 2, for 2 dimensions. And I want to show you some nice things that actually, in 2 dimensions, connects with complex variables. Well, one thing we can never forget, right, is that if you have an analytic function in complex variables, the real part and the imaginary part are harmonic functions. They satisfy Laplace's equation because of Cauchy-Riemann equations. Okay? So you're going to see that this integral here reminds us a little bit of what kind of things we do, with residues, for example. Okay? Reminds us a little bit. So look what I'm going to do. So I want to see, look, and actually you can do this in complex variables, and it's quite interesting. We don't see this actually. I don't think we quite see this usually in typical complex variables course, which is you take the Cauchy integral, right, which is the integral like f of z over w minus z dz and so on, and take the w and let it cross the border. Things blow up. But it blows up in an interesting way. And this is a little bit what we're doing. See, this looks a little bit like, if we were in complex variables, this looks a little bit like the integral around the contour, and we're going to take our point and let it hit, right, the boundary. Okay? All right, so let me break this integral into the parts, which is this. This is L epsilon plus minus epsilon L u of x d log of r dn dx parentheses plus the complicated, but plus the contour part. Not the x, here's the s. Okay? Now look how complex variables is kind of going to be useful here. Let's remind ourselves that log of z, so let z be complex, log of z is equal to what? Is log of r plus I argument of z. Right? That's from complex variables. Okay? Where the same thing, theta is equal to argument of z, just to remind you, which is the arctangent, y over x, and we can think of z as r e of I theta, if we're using polar coordinates in the complex plane. Okay? So we also know that this is the same as u of xy plus I v of xy, which means that v is a harmonic conjugate of u, right? And therefore, they satisfy Cauchy-Riemann. So therefore, we have Cauchy-Riemann, which is u of x is equal to v of y, and u of y is equal to minus v of x. Okay? And this comes out of the fact that of the complex derivative. And I hope you remember this from complex variables. Let me remind you of this. So this is, if f is our analytic function, right? This comes out of the fact that dv dz is equal to df dx, which is equal to minus I df dy, because the complex derivative has to work in every direction, right? So it has to work on the x direction, and on the z direction. That is, if dz is equal to dx, or if dz is equal to I dy, right? That's how we get this. Okay, so from this, excuse me. Oh, there's another thing too, which is good. It's a problem actually in Fritz John, is that Cauchy-Riemann also works in this way. Du dn is equal to vs, and du ds is equal to minus vn, where this is a tangential derivative, and this is a normal derivative to a curve. To some curve, okay? So the Cauchy-Riemann also is satisfied in that fashion. So therefore, the nice thing about all this is that I can write, let me write here, that this no, it's going to be too messy. Let me write it on the other board. And I think I will be able to finish this at a good point. So, yeah, let me write. So therefore, this is nice. Look, therefore, arc tangent of yx is the harmonic conjugate of log r. And therefore, I can write this integral in a way that becomes nicer to me, which is which is equal to, there is some ux, that ux, integral from 0 to theta d arctangent ds plus order epsilon which is equal to pi u x bar plus order epsilon, because this is just the integral of the arctangent from here to here, from 0 to pi. Okay? So therefore, the general result is that as epsilon goes to 0 and xi, right, went to the boundary, that u of x is equal to u of x dk dn plus, no, not plus, minus du dn k ds for x at the boundary, and also, I should put it like this, sorry, x bar at the boundary, and k is actually k of x, x bar. Okay? And actually this theta, and then of course I'm not doing the whole proof, where this theta is equal to pi. If x bar belongs to the boundary at a smooth point, and theta is equal to internal angle if x, right, belongs to the boundary at a corner. So the idea is this. Let me make maybe a, if this is my domain, gamma, right, and x bar is here, the internal angle is pi. So we can think of theta always being the internal angle. And here, it's theta. So basically we can use Green's identity and let xi move to the boundary. Okay? And if, let me release my hands and our time, I think this will be the good point to stop. And if we move to the boundary and the boundary is smooth, right? Locally, a smooth boundary looks like this, like a little line segment, right? And that's why I did this calculation, and we see that then we get pi, because we can use the arctangent, blah, blah, blah. We get pi, and the pi comes out, right? So the internal angle is equal to pi, right? We got it from here. It's a little more complicated if you have an internal angle, a corner. But you can see that, right, that you can see that it's kind of intuitive that in all cases here, theta is the internal angle, be it the internal angle at a smooth part, which is pi, or the internal angle if you have a corner. Okay? Now, finally, if this expression here is, let me write it here, is a functional relation. So we have deduced a functional relation between the Dirichlet and the Neumann data. Because look, this is Dirichlet, this is Dirichlet, and this is Neumann. Okay? So, this is used sometimes numerically. Sometimes it's a bit ill-conditioned from the numerical point of view. I don't know what if you know what ill-conditioned means, but it's like sensitive to perturbations to some extent. But look at this. If I can do this integral over the boundary, and for the two-dimensional case, this is a line integral, right? That's the right notation for a line integral. So if I do an integration, let's think of the 2D case like this, over the integral. And if I approximate this integral, this is going to be like this. If I approximate this, let me see where I can write this. Let me keep this here. So if I approximate this for a matrix and a vector means this x is points like this over the boundary. So the vector x are these values here, okay? Look at this expression here, numerically, is going to look like this. It's going to be theta. No, but the theta might change to point. So it's going to be some diagonal matrix times the vector u is equal to a matrix let me change my notation. Let me call this vector f for Dirichlet data, okay, as I used before. Okay, so Dirichlet data, a vector f. This is going to be a matrix m1 times the vector f plus a matrix m2 times the vector g. So g is the Dirichlet data, and f is the, g is the Neumann data, and f is the Dirichlet data. So do you understand this notation I'm doing here? Right? So this is a diagonal matrix with a theta multiplying the u's, okay, depending on what angle is here. If it's a smooth domain, this is pi times the identity, right? If the domain is smooth. But if I have a corner, it's going to be different from pi, okay? So this diagonal matrix times the Dirichlet data is equal to some matrix that has to do with the discretization of this guy times the Dirichlet data. And this is this matrix, M2, times this data. So this equation here is a way that says me the following. If you give me a Dirichlet problem, I know f. So my linear system will be M2 times G is equal to B, where B is this part here. If you give me a Neumann problem, I know G. So my problem is going to be D plus M1 F is equal to B. And I have to solve this on the computer. This is AX equal to B, AX equal to B. So let me finish up the lecture with a very important thing. This equation tells me that there is a functional relation between the Neumann data and the Dirichlet data, right? If I cannot, as I mentioned, I cannot impose one and the other off the top of my head, right? They are related. And who controls the relation? The Green's function, right? I showed you before that if I know both of them, I've solved the problem. the question is that I never know both of them because I cannot impose both of them, right? But if I know one of them, what this expression tells me is how I can get the other one. Sometimes it's not an easy problem, but still, formally, I can get the other one. And once I get the other one, I do that integral, and I know the solution anywhere inside. So this is what's called a boundary integral formulation, because I'm only playing with the boundary. And at the end, I'll know the solution inside. Okay, so this is a different way, non-typical way, of looking at Laplace's equation from a different perspective, from an integral perspective. Okay? So I think this is a good point for me to finish, and we'll continue playing with these things a little more as we go along. Okay, I'm going to come back next class to Green's function. Right now I talked about the free space Green's function, which I didn't quite explain what it was, but it means it's a Green's function that doesn't care about the boundary, right? There's no information about the boundary in the Green's function. But there are situations, for example, a ball, where we can make the Green's function satisfy boundary conditions, and that helps us, blah, blah, blah. We'll see this next time. Okay, so I'll finish here.